Okay, so what are satellites? Satellites are, let's say this is a planet, and let's say an object goes around that planet. So this object is called a satellite of that planet. So anything that object orbits around another object is called the satellite of that object lah. Okay, so that means this object is a satellite of this planet lah. Now, how do satellites travel? They are actually traveling in a circular motion, right? So if they travel in a circular motion, that means it must have what force? Centripetal force. So if it has centripetal force, that means it needs another force to provide it. Because centripetal force being a resultant force cannot exist on its own, it needs to have another force that provides the centripetal force. So what force exists between the planet and the mass? Gravitational force. So therefore, the first equation that you can use is gravitational force provides the centripetal force. So you can either write as gmm over r squared, which is the gravitational force, equals to mv squared over r, which is centripetal force, or you can write in terms of omega. That means you can also write your centripetal force in terms of omega. So your gmm over r squared equals to mr omega squared. Now it's up to you which one you use, and depends on the question whether they want in terms of v omega. Both also possible lah, right? So don't forget this is the r, distance between the object and the planet. Okay. Now moving on, if you want to solve satellite orbit questions, when we use this equation, now when exactly can we use what kind of satellites are we talking about? We're talking about those satellites they just go round and round and feel weightless. Example, if you were in one of the satellites of the Earth, for example, let's say you were sitting in the International Space Station as it orbits around the Earth. So the International Space Station orbits around the Earth. You would see movies or videos of the astronauts inside the space station. They are floating. That means they are weightless. But they are still not that far away such that the gravitational force is zero. You still have a gravitational force acting on them. But why do they float? Why they don't have a weight? If we compare to Earth, you see, we are actually at the equator. Let's say this is the equator of the Earth. So we are standing at the equator, right? So when the Earth spins about its axis, because the Earth spins about its axis, we are actually also undergoing circular motion, right? So can we then say we are like this satellite? Can we say that we are also the same as this satellite, since we are also moving in a circle? But then if we are the same as the satellite, then how come we feel a weight, whereas the satellite here does not feel a weight? In fact, any object in the satellite will feel weightless. So what is the difference? The difference is, for this satellite, their entire gravitational force is used up as centripetal force. There's nothing left over. So therefore, they don't feel any weight. Because your centripetal force, you don't feel it. Like now, when you're on the equator, do you feel yourself moving in a circle? Do you feel a centripetal force? You don't feel it. So if your entire gravitational force is already used up by centripetal force, you have no more gravitational force left over, then you will feel weightless. But we are nearer to the Earth. Our gravitational force is stronger than the satellite here. On top of it, we are moving slower than the satellite here. Example, let's say you're talking about International Space Station. Do you know that they actually go around the Earth many times in 24 hours? So it's not just one round around the Earth 24 hours. So for them, they will see sunrise and sunset many times in 24 hours. So they're moving very fast. So when they're moving very fast, their centripetal force is high, their gravitational force is lower than Earth, so their entire gravitational force is used for centripetal force. But since we are nearer, our gravitational force is bigger, we are moving slower, our centripetal force is much lower, so only part of our gravitational force is used for centripetal force. We have a lot of gravitational force left over, and the gravitational force that is left over becomes our weight that we feel. So for us, we cannot use this equation because our entire gravitational force is not used up for centripetal force. So you must be aware when you use. You cannot say anything that goes around the Earth can use. It must go around the Earth and be weightless. Then you can use these formulas. Okay? Now, whenever you use this formula, you need to pair it up with another formula in order to finish solving lah. If you're using GMM over R squared equals mv squared over R, you need to pair it with V equals to 2 pi R over T, which is the formula for a circular motion as well, because for one complete revolution or one round, your distance traveled will be the circumference 2 pi R and the time taken is period. But for omega, we need to pair it up with omega as 2 pi over T, which is also seen in circular motion. That means for one complete circle, the angular displacement is 2 pi radian and the time is called period. So if you pair up this and this, or this and this, you will be able to solve all the satellite orbit questions. Now, we also need to derive from these two equations Kepler's third law, or from these two equations Kepler's third law. So I'm going to show you how I'm going to derive it and what's the significance. Last one. So now let's say we want to derive Kepler's third law for omega also can. So we start from GMM over R squared equals to MR omega squared. Then we can cancel one M, but we cannot cancel the R because one is on top, one is on the bottom. So the omega squared equals to GM over R cubed. Now, so your omega will be square root GM over R cubed. Now, we also have the second equation, omega is 2 pi over T. So we equate both of them. So the 2 pi over T equals to square root GM, just write nicely, GM over R cubed. So you get 4 pi squared T squared equals to GM over R cubed. So you get T squared over R cubed equals to 4 pi squared over GM. Also, you can get the same equation. Alright, so this proves that remember these two sets of equation, which is this and this, can give you the same equation as Kepler's third law. Alright, so it is important to know the derive because the exam they'll ask you to derive.